Hey, Castle here, and welcome back to Memphis Communiversity. Today we're talking about volumes by rotation. This is a pretty specific topic, but it goes under the area and volumes unit, so make sure you check out all the videos and understand everything there is to know about area and volumes before you move on to doing these practice problems about volumes by rotation specifically. As always, this worksheet and the answers are in the description below, so you can go click those and follow along or just do this on your own for practice. So I'm just going to get started kind of going through these givens, and we have a graph that's given, and it says that we have R, that shaded region, is enclosed by the f of x function, which is that curved line, the y-axis, and the horizontal line y equals 1. So you can see those with dotted lines. Oh, and the vertical line x equals 1. Those x equals 1 and y equals 1 are represented by the dotted lines there. So these are just the givens, and I'm going to draw this graph on every single example so we can keep referring back to it. But the question is always going to say, find the volume of the solid obtained by rotating R around a specific line. So we'll get to these examples and you'll see what that looks like, but basically we're going to be drawing different shapes, like a box to represent that solid R, that shaded region, and just following pretty much two different formulas to figure out that volume. So again, this can seem a little tricky at first, but once you do the examples, you'll get the hang of it. Let's get started. Okay, so on the first one, you can see that we're finding the volume of the solid obtained by rotating R around the horizontal line y equals 1. So you can see that in the dotted lines here. And you can also see that I drew this, I'm going to refer to it as a box throughout this video, which is just that rectangle. And I have it as the dx rectangle. So that kind of just represents the shaded area R, and we're going to be rotating it around that horizontal line y equals 1 to figure out the volume. So let's look at this. You can see that I drew a box perpendicular to the rotational axis, which in this case is the horizontal line. So I have what's called a dx box, which is just a box that stands up vertically. Let's see if it'll focus. Okay. So I've got that perpendicular box that represents R, and what I'm doing here is drawing this circle, and that pretty much represents the part of that box that's touching the rotational axis. So you can kind of see right here, since the rotational axis isn't a function, isn't a function like that f of x function where it's curved, it's just a straight across line. Every part of that solid R and every part of that little box that I drew is touching the line completely. So what we're doing is drawing this circle that represents that, and I'm going to find the radius of the circle. And you'll see why I'm doing all of this once we look at the formula. I haven't showed that yet, but I just want to do all of this first. So the radius in this case, and in all of these cases where you have the dx box, is you're going to have top minus bottom function, which here your top function is up at the top of that box, and it's f of x, which is given before we have the problem. And then at the bottom you have 1 because we're rotating it around the horizontal line y equals 1. So to get that radius, I'm just going to plug in that f of x function and then subtract 1. Okay, so now that we have all of this information, I'm going to show you the formula that you use whenever you have a circle like this that you're looking at, and whenever you have a solid that completely lines up against the rotational axis. So I'm just going to skip ahead a little bit so that you can see this formula. Okay, here we go. This is the formula. I have volume, which is what we're trying to find on all these problems, equals pi, and then you have integral a to b, so the different x values that you're using, radius squared. So remember that an integral, and when you're looking at a graph, is going to be the area of that graph. So we have this circle here, and we found the radius doing top minus bottom, and you can see that pi r squared is the area of a circle. So we have the integral of pi r squared, and I just put that pi out in front because that makes it easier when we're doing all of the work. And so you basically just have the integral of pi r squared In this case, I wrote disk because we're going to get to some problems later where you have a circle within a circle, and the formula for those is a little bit different. So I'll refer back to that later. But right now we're just going to follow this formula with the information that we have given and find the answer. So I'm going to write out all of this. I've got my volume equals pi. You always have pi in front when you're doing volumes by revolution. Every single time, you don't want to leave that out. And then I'm looking at 0 and 1 because that's where my x values start, and then they end at that x equals 1 line. And then top minus bottom squared. So we found our top minus bottom over here, looking at the graph. And then you want to make sure you square that. Okay, so I'm going to show you this being plugged into the calculator to find the answer that I'm writing out now. You can't see that, but pi over 2 is, let's see, 1.571. So let me show you that in the calculator. Okay, so you can see I'm just typing this in. My calculator might look a little bit different from yours, but if you take calculus, you could have a calculator that can do this. So I'm just kind of typing in everything that I wrote. I'm showing you this because I want to show that you have to be really careful with parentheses when you do this. Making sure that you have all your parentheses in the right place is really important, because if you get to the calculator step and you have everything right, you don't want to get it wrong just because of the way you typed it in. So there is that answer, and let's go ahead and move on to the next thing. Okay, the second one is a little bit different because instead of being rotated around the horizontal line y equals 1, we are rotating this solid around the x-axis, which you can see is right here. So our gray area, that R that we're looking at, actually isn't fully touching the rotational axis. So I'm going to show you what we have to do here because this problem is pretty different. So I'm going to go ahead and draw my dx box because we are still rotating around a horizontal line. But because we have space between that shaded region, or the R region, and the axis that we're looking at, we have to draw what I'm going to refer to as a connector. So the connector just represents the space between the bottom of the place where we have the area, the bottom of R, and the axis, the rotational axis. So we have that connector, which changes what we're going to do later in the problem. So I'm just going to go ahead and label that. So we still have this dx box, so we're still going to be working on finding a radius with top minus bottom. And what I'm going to do is draw that circle, which I would recommend that you do. I think it's pretty helpful as you're doing these to kind of draw the circle just to visualize the space that you're looking at. So I drew that circle that represents that solid area, R, but then I'm going to draw a circle within that that represents that connector. And I have to find the radius of each one. So the first thing I'm going to do is find the radius of the whole thing, which just means the top minus bottom of both the box and the connector. So in this case, I have, and I'm calling it the outer circle, and then I'm going to call that smaller circle the inner circle. So the first thing I'm finding is the radius of the outer circle. Let's see. Okay, so the radius of the outer circle is the top minus bottom of this whole thing, the box and the connector. So I'm going to start with that f function as the top, and then the bottom is 0. But the radius of the inner circle, that connector, actually is just top minus bottom with 1 up there and 0 down there. So since we have two different radii that we're looking at, we are going to use a little bit different of a formula, but the basic foundation of the formula is the same. You're still finding integral pi r squared. So I'm going to skip ahead so that we can look at this formula. Okay, so here's the formula I'm going to use on these ones where we have a box and a connector, and it's the second and final formula that I'm going to show you in this video, so the rest of them are just practice with plugging things in. So you still have the basic formula where you have that pi that you can't forget, and then integral a to b, but in this case we are going to have outer radius squared minus inner radius squared. So the outer radius we found was that f of x minus 0, and the inner radius was 1 minus 0. So we basically still have radius squared, but because we are using two different radii, two different circles, because we have that box and that connector, we have to use this formula, which I call the washer formula, as opposed to the disk formula that we did earlier. And I just call it that because this looks like a washer. It's got a hole in the middle. You can call it the donut formula or whatever you want. But just remember that this one is pi integral outer squared minus inner squared. So I'll show you that in the calculator. Okay, I'm typing this in now using the graph that I was looking at earlier. So I've got pi. I'm going from 0 to 1 because that's where my solid area, that R area, starts and ends. And then I'm doing, again, I have to use a lot of parentheses here, but try to keep up with those so that you don't get messed up, especially when you're doing things squared. Parentheses are really important. So I'm doing that f of x minus 0, that outer squared, the outer radius, and then I'm going to subtract the inner radius squared. And this is where a lot of people get messed up with parentheses, so just make sure you use all that you need to. And then when I do that, it's going to give me 11 pi over 6, and then I'm just going to make that into a number and get 5.759. So that's my answer for number 2. And these next few are all pretty similar to 1 and 2, and so we'll get practice kind of being able to distinguish which formula you're using and the tricks that you need to watch out for. Hey, I'm done here now because we are on number 3. And the different thing about number 3 is that now we're using a vertical line instead of a horizontal line. So the basics stay the same, but in this case, we're actually going to be dealing with y values instead of x values. For example, when we had a to b on those formulas previously, we were going from this x value 0 to this one 1. But now we're doing everything in terms of y because we're dealing with a vertical line. So remember, your box that you're drawing has to be perpendicular to the rotational axis. So instead of having a dx box here, we have to have a dy box. So just remember, if your rotation axis is vertical, everything is in terms of y. If your rotation axis is horizontal, everything is in terms of x. And that just matters when you are doing that a to b. And then also sometimes you have to switch around your f of x function, which we'll see later, so that everything's in terms of y. So let's go ahead and draw this. Since we're dealing with the vertical line x equals 1, this is not going to be a washer or donut formula. We're just going to be dealing with one disk because this R touches every point on that axis. So we're going to find the radius of this circle, which, okay, so since we're dealing with terms of y, instead of saying top minus bottom, I'm going to be saying right minus left, because we are going to be going from this rotational axis to the f of x over here where the box ends. So to find our radius, we're doing right minus left. Our rightmost function is x equals 1, and our leftmost function over here is, this is when we have to change up the f of x. It's the f of x, but to do it in terms of y, we are going to have to switch it up a little bit. So the f of x that was given originally was square root of x plus 1, and to make that in terms of y, we just have to move things around, and we're going to end up getting y minus 1 squared. Let me get that written out. Okay, there it is, y minus 1 squared. So we've got right minus left, and then we're going to go back to this disk formula that we used earlier. You can't see it now, but I will just go ahead and plug everything in. I'm going to have volume equals pi, don't forget the pi, integral a to b. In this case, I'm doing 1 to 2 because I'm using those y values, and then I'm going to do my radius squared, which we have written out there. So remember here, what is a little bit tricky is that you have a squared here because of the f of x function, but you still have to take all of that right minus left, and do that squared. Okay, so now that we've got everything plugged into the formula, I'm just going to go ahead and write out the answer. I'm not showing my work on my calculator this time, but later I'll show you some more stuff on the calculator that you need to know. So in this case, our answer is going to be 1.676, and we can move on to number 4. Okay, so here I'm rotating my solid R around the y-axis. So I've got that box, but since we're using that y-axis, y equals, or that x equals 0, I have to have a connector to represent that space in between our r and our y-axis. So this one, we are going to be using a washer formula or a donut formula. And so remember, we're going to be finding the outer radius, which is the radius of our whole thing, our box and our connector. And we're going to have the radius of our inner, which is just our connector. So in this case, I've got my outer radius, which is right minus left of the whole thing. So, oops, I messed up there. Let me fix that. Okay, here we go. Fix my mistake there. So our radius of the whole thing is going to be 1 right here minus 0 going all the way to the end of the connector on the left. And then the radius of our inner circle is going to be that f of x function to the right of the connector, and then the 0 to the left. So again, we're going to be using that big formula that we talked about earlier. There's my right minus left. We're going to be using the formula that has pi integral a to b outer squared minus inner squared. So this is why I think drawing these circles every time helps a lot, because it kind of helps you keep the outer and the inner and all of that, keep that organized as you plug it into the formula. So let's go ahead and write all this out, and I'm going to move my face up here so that you can see everything. I've got volume equals pi 1 to 2. Remember, everything is in terms of y. Outer squared, there's my outer, minus inner squared, and here's my inner over here. Remember, again, when you're typing that into your calculators, keep all those parentheses straight. Again, I'm not showing my work on the calculator this time, but the answer is going to be 4 pi over 5, which as a number is 2.513. So hopefully this is starting to make a little bit more sense, but we have a whole page of examples if not. All right, I've got those formulas that we talked about earlier written at the top of this page, so just take a minute to review those if you want before we move on to this next graph. I'm going to start marking some things up on this graph at the top. It's pretty similar to the one before, even though the graph looks different. We're still using the same formulas, all of that. So we've got a region enclosed by f of x, which I wrote out there, and g at the bottom, and we're going to be finding the volume of a solid obtained by rotating r around a specified line. So the first line that we're talking about is the x-axis. Hopefully you can see all of this work. I think I'm going to move it down a little bit. Okay, we are looking at the x-axis on this one, so I'm drawing my little dx box because our x-axis is horizontal and we need to draw that box perpendicular to the rotational axis. And since it's the x-axis and that's further down than r actually goes, we have to draw one of those connectors to represent that space in between r and the x-axis, which means we're going to have two circles and we're going to be using our washer formula. So let's start with that bigger circle, and we're going to be doing, again, we're back to doing things in terms of x, so we're doing top minus bottom, not right minus left. And in this case, our top of the whole thing is up here with f of x minus 0 to the bottom of the connector. And then when we do our radius of this little connector, the top is going to be g right here, and then again 0 at the bottom. So now we just have to plug everything in to the formula that we're given. And there's one thing on this one that's a little bit different, so when we get there, I'll show it in my calculator. But this formula is pi integral a to b is what I'm going to write right now, but that's going to change in a minute. And we're doing our outer squared minus inner squared. And right now I'm just keeping things f and g because you're going to be doing this in your calculator, so you don't have to write out all of that on paper. And I'm just going to write that out. Okay. Okay, you probably noticed that when I was doing that work just then, I had on my integral a and b, but we have to have points there, but those points aren't given to us, so we are going to find them using our calculator. So right now I have my graphing calculator up, and what I'm going to do is just type in that f of x and g of x function that was given to me at the beginning. So here I'm typing my f of x, And once you type those in, you should get a graph that looks exactly like the graph that was given. So there's the top function of my graph, and now I'm doing g of x. Remember, what we're trying to find is the a and b, those values, so that we can plug in all of that to our calculator and get a final answer. So what I'm doing now is I'm finding the intersection points of these graphs. So I'm going to analyze graph, intersection, and what I'm going to do is take my dotted line and put it before that point where I see the two graphs meet, and then a little bit after. And you can see a point show up right there. I have my x value as negative 0.813. So you want to write that down or remember it or put it somewhere, because that's going to be my a. And then when we do the same thing again, you get another x value that is, you can't really see it there, but it says 0.945, and that's going to be my b. So I didn't write out all the work for this, but you can see down here that I have that a and b. And after I find those intersection points, what I'm going to do is plug in my negative 0.183 and my 0.945. And when I plug all of that into my calculator with my f of x and g of x functions fully written out, what I'm going to get is, in this case, I'm going to have 23.352. And that's my answer. So let's do another problem and practice using those same intersection points. Here we're looking at the horizontal line y equals 3. So we're going to go ahead and write that in. That's going to be above the graph. So I'm doing a dotted line there to represent my horizontal line y equals 3. You can see that r is not touching the horizontal line completely, so we have to draw a connector. This is going to be one where we're using an outer and an inner radius. So to find my outer one, I'm going to do top minus bottom of the whole thing. And I want to point out here that so far the top function has always been kind of at the top of this, somewhere on the box. But when I say top minus bottom, that actually just means really geographically, wherever it is on the top is where you're going to start. So in this case, it's touching the connector, but the top of our whole function is still 3. And then you subtract g because that's at the bottom of the whole thing. And then I'm going to draw a smaller circle, which is my connector, and the top of the connector, as you can see, is 3, minus the bottom is going to be that f function. So we're going to use the same formula as before. I will move myself so you can kind of see it. There we go. Using pi integral a to b. And now we know that our a and b are those intersection points, which are negative 0.183 and 0.945. I just didn't write them out right there. And we're going to do outer squared minus inner squared. And what we're going to get on that one is 23.273. All right, on to our final graph. On this one, we've got a region enclosed by the functions y equals 2 up here and f of x equals 2x squared right here. So again, all our questions are the same. We're rotating r about a specified line and finding the volume of that solid. So let's just get started with number 7. We've got y equals 3. So I'm going to draw in my horizontal line, y equals 3 up at the top there. And since that's a horizontal line, we're going to draw our box perpendicular to it. And since it's not touching the top of R right here, we have to draw a connector to represent that space. So we're going to have two circles that we're finding the radius of, starting with our bigger one. And we have to find the top minus bottom of the whole thing, connector and the box. So the top is going to be 3, and the bottom is going to be that f of x function, 2x squared. Okay, and I've got the radius of that connector is 3 minus 2. As you can see, I've got the top minus bottom there. So when I'm plugging it into all of this, I'm going to have pi, and I'm putting -1 and 1 right now, but in a minute after I write this out, I'm going to show you how I got those in the calculator, finding those intersection points. So I'll show you that in a minute. But let's just keep looking at this. I've got my outer squared with that radius of the whole thing minus inner squared with radius of just the connector. And that's going to give me 30.159. So now let me show you in the calculator how I got a and b to be -1 and 1. Okay, so I'm pretty much just doing the same thing here that I did when I found intersection points earlier, starting by typing in the two functions that I was given, which are 2x squared and 2y equals 2. And I should have a graph that looks pretty much like the graph given. And then I'm finding those intersection points by doing intersection, taking that dotted line a little bit before the point and a little after, and I've got -1 and 2. Since everything is in terms of x, the -1 is the one that matters there because that's our x value. So write that down or remember it. That's going to be your a. And then your b is going to be that 1 right there. So that's where you got the -1 and the 1 for the problem that we just did. And there it is. You can see I've got that -1 and 1 there. And since on this next one, we're still using the same r, those intersection points are going to stay the same. So let's do this one. This one we're rotating around the x-axis, which you can see you're going to be using a dx box because your x-axis is horizontal, but you're going to have to add a connector right there because you've got some empty space between r and the axis. So we're going to be drawing our two circles. Our big radius is the top minus bottom of both the rectangle and the connector, so we've got 2 minus 0, and then our inner radius is the top minus bottom of just the connector, so we've got the f minus 0. So this one's pretty similar to the one we did before where we're doing pi, -1 and 1 with those intersection points, and then outer squared, so 2 minus 0 squared, minus inner squared, which is f minus 0 squared. Again, when you're typing this in your calculator, be super careful with parentheses. I'm not showing it in my calculator right now, but you will have to do this in a calculator. And you're going to get 20.106 for this one. So that's the last of our examples. And I'm just coming back up here to show those formulas one more time so that you can review those. The formulas are pretty similar, but it just matters whether you have one of those connectors or not. So hopefully this video was helpful. If it was, like it, subscribe to this channel because there are a lot more videos for calculus students, whether you're in high school or college, and go ahead and check out those other videos. Thanks for watching.